Okay, we're moving right along in our transformations unit, and as you can see, we're going to talk about rotations today. That'll be our focus. Kind of like the Ferris wheel here. You're moving from one spot to the next, rotating around a common point. So we'll talk about how we can represent that in geometry and especially on the coordinate plane. Okay, so here are some examples of rotations. Notice we're rotating around point C. So this line AB gets rotated. Looks like we're going counterclockwise. And notice as we rotate that point, as we rotate it around point C, we'll maintain the same angle. Every point gets rotated the same amount. So that angle there is the same as this angle. And notice it's the same distance from that center, from that point of rotation. No matter where I go, if I'm using this one, rotating around point C, notice B to B prime is the exact same angle as A to A prime. And those points, the image points along with the pre-image points, are the same distance away from that center of rotation. Notice these examples are not rotating. This one is a reflection. Here we have a translation. This one here is a translation. Here we have another reflection. Okay, so in order to be a rotation, each point has to move the same number of degrees in the same direction as all the other points. So let's take a look at now how we can draw a rotation of 180 degrees of triangle ABC about point P. So we can use our protractor for this. So the first thing we do is we connect our segment A to P. So we draw a line connecting the first point to our point of rotation. Then we form a 120 degree angle. And we're going to go counterclockwise, just in general whenever it says rotation, unless it says otherwise. So we'll create a line, 120 degrees. It doesn't matter how long the line is at this point. Just draw a line at 120 degrees. And then we'll measure the segment PA and create a congruent segment here. So here's where you would figure out if this line is too long. You just put the point on however the distance is from PA, make that the same to PA prime, and then you could just erase the rest of that segment. So now we have congruent segments, 120 degree rotation. You then do the same thing with point C and point B. Make those points 120 degrees and equal distant. And then it should appear like it is here. Now let's take a look on the coordinate plane. As we're going from blue to the red, what is occurring? Well, we can see that it's a rotation. And we're going counterclockwise. How many degrees are we going in this figure? Well, it appears that we're going 90 degrees. I can check and compare my points. Looks like I have a right angle there between any of the points that I connect. So all the points are going 90 degrees. So we've got that counterclockwise rotation. Now, using coordinates, let's figure out what the coordinates are so we can compare. This point is at 2, 0. And this one's at 0, 0. Here's that this one's roughly at about 0.8, -2. And let's compare the other points. 0, 0, 0, 2, and 2, about 0.8. So notice as we compare these coordinates, what is happening to those points? Well, it's hard to tell with these because they stay the same. Here we're going from 2, 0 to 0, 2. So it appears that they are flipping. The values flip. And if that works here, 0.8, -2. that flips, but then notice this point, the y coordinate becomes the opposite, changes signs. That happens here too because 0 becomes its opposite, isn't affected. So the rule then we would say is xy becomes opposite of y, x. We'll take a look more at how we come up with those rules with some more examples here. So let's take some examples of triangle rotated 90 degrees, 180, and 270. I'd like you to list the coordinates for those points and see if you see a relationship with those rotations. So take some time to do that. Pause it and start it again when you're ready. Okay, so these are the coordinates that I came up with. You can check to see if those match with yours. If I did something wrong, please let me know. But let's take a look at the 90-degree rotation. Look what happens to the coordinates. We want to see if we can come up with a rule for what's happening when we're rotating 90 degrees. Looks like the coordinates are flipping. And this first one, the new x, becomes the opposite. So we can list it as, that was like our previous example. Coordinates flip, so the new x is what we had previously for the opposite of our y. Our new y coordinate was what we had for x previously. See if we can come up with a rule for the next one, the 180-degree rotation. 3, 4 becomes negative 3, negative 4. 1, negative 2, negative 1, 2. 5, 1 becomes negative 5, negative 1. Looks like nothing's changing places, but the x is now the opposite. The y is now the opposite of what we had for y originally. In 270 rotation, 3, 4 becomes 4, negative 3. 1, negative 2 becomes negative 2, negative 1. 5, 1 becomes 1, negative 5. It appears that the values are flip-flopping. And it looks like we have a negative here. So 3 became negative 3. So it looks like our x is becoming opposite of x now in the place of the y, where the y coordinate should be. Okay, so those are the rules for rotating, and we can list all those together in one spot. If we want to put those same things down, it's just what we had before. It's just a different way to write it. Now we're saying A and B if X's and Y's get you confused. So if we're rotating 90 degrees, they're just flipping places, and the first one becomes opposite of what we had. If it's 180 rotation, both of those become opposites. If it's a 270 rotation, we flip the values, and our y coordinate becomes the opposite of what we had originally for A. So those are the rotation rules that we can apply. Remember, you can just keep in mind what's happening. Remember, they're going the same degree each point, and they're maintaining the same distance. But sometimes we can apply the rules to make that go a little bit quicker. So let's rotate using the coordinate rules. Rotate this quadrilateral 270. So graph it and then rotate it. Pause the video and start it again when you're ready. Okay, so I graphed the original quadrilateral and I rotated it 270 degrees about the origin using the rule xy becomes y opposite of x. Listed my original coordinates in a table. Made it easier for me to switch over. So I just took the xy and I flip-flopped the y and the opposite of x. And then I graph those points on the coordinate plane. Notice if it goes around the point of rotation, r to r prime, that's a 90-degree angle there, so counterclockwise would be 270. T to t prime is also 90. S to s prime is also 90. So it maintains the rules of rotation. So what would happen if we don't know the value of x or y in this figure? We know it's a rotation and it's 110 degrees. So if we wanted to find the value of x or y, asks us to find y. Let's take what we know. Well, in a quadrilateral that's been rotated, we know it maintains congruence. So those will be congruent. These will be congruent. This segment and this segment. So if we want to find y, those segments will be congruent. Since I have two variables, I can't do much with that right now. I see another x value here, and that one is congruent to 6. So if 3x is 6, that means x has to be 2. I can plug that into this equation, 7y. 3 times 2 is 6, plus 1 is 7. Therefore, y equals 1. So I just solved that one, maintaining what I know about the rules of rotations. Similar to rotations, we'll talk about rotational symmetry. Rotational symmetry is directly connected with rotations. So we have a center of rotation. It's like in this pinwheel here. If we rotate 45 degrees, that's what we get, 90, 180. We talk about a figure having rotational symmetry if it can be mapped onto itself by a rotation of 180 or less, about the center of the figure. So notice if I move this figure 90 degrees, I'm back to the same that I started with. And we rotate again, 180 degrees, same spot. So we would say that that has rotational symmetry of 90 degrees or 180 degrees because that maps it back onto itself. 45 wouldn't be correct because it's a different representation here. So see if these three figures have rotational symmetry and be ready to describe that by the number of degrees that it rotates if it has rotational symmetry. So pause it and start it again when you're ready. The parallelogram has 180 degrees rotational symmetry. If I were to rotate this figure, notice it's a 180 degree turn before I'm back in the same position. Another 180 rotation back again. So in a full 360, I'm in the same spot twice. So 360 divided by 2 gives me 180 degree rotation. The octagon, if I rotate that 45 degrees, notice I'm in the same position 8 times in a full rotation. So 360 divided by 8 gives me 45 degree rotational symmetry. Trapezoid doesn't have any rotational symmetry because it takes a full rotation to get back to where I started. So 360 divided by, I'm only there once, is 360 degrees. So I have to go a full 360 degree rotation, which doesn't classify as rotational symmetry. It has to be 180 degrees or less. All right, once again, we'll do some bonus geometry with the accelerated group, learn more about the matrix. But those of you who are in the normal pace, you learned about how to do rotations, what the rules of rotation are on the coordinate plane, so you can get to work on the practice then in class.